In a perfect world, calculating torque would be very easy because all the forces would always act perpendicular to the axis of rotation, but unfortunately, that's not always the case. More often than not, in the real world, these forces that are acting in relation to this hinge or to an axis of rotation are actually non perpendicular. So they act at some kind of angle. So as you can see here, this force is not acting perpendicular to my axis of rotation or my fulcrum over here. This is actually acting at an angle. And that changes things for us because torque is calculated by multiplying the force times the perpendicular distance. So what we need to take a look at is we actually have to resolve this into horizontal and vertical components. So while this force is being pulled at an angle, since it's pulled to the side here, you can hopefully see that some of this force is trying to pull this beam to the right, and some of it is trying to pull it up. So when you combine the upwards and the rightwards force, that's when you get this combined force at a particular angle. And if you also look, the force that's trying to pull it this way is not perpendicular to the fulcrum. It's actually located along the same line, so that'd be 0 degrees. But the upwards force, the vertical component, the part of that force that is trying to pull up is acting at a 90-degree angle to this fulcrum. And I'll show you how to go and find those values. We just have to use a little bit of trigonometry, a little bit of right triangle geometry. So here I've redrawn my force acting at some angle. And all I've done here is I've drawn in, there's some kind of x component, some kind of horizontal component of that force trying to pull the beam to the right. And there's some kind of vertical component. Part of this force is trying to pull that beam straight up. So I have an x and I have a y, or a horizontal and vertical component. And if I set up a right triangle, like so, I can use SOHCAHTOA and my trig functions to figure out what my horizontal and what my vertical force may be. So here I've used sine, which is just opposite over hypotenuse. Therefore, my opposite side is my Fy, my hypotenuse is F. So if I rearrange this equation, I can find that the vertical component is just the magnitude of this force multiplied by the sine of this angle. Likewise, if I want to find Fx, that's the adjacent side, so I'll use cosine. Cosine of theta equals adjacent over hypotenuse, which in actuality is the x component, the horizontal component, over the actual force. When I rearrange this, I will get that the horizontal component is equal to the force times the cosine of that angle. Typically, the vertical component will be found using sine, and the horizontal component will be found using cosine and multiplying by that given force. This is not always the case, so just be careful to set up your triangle and make sure that the trig identities are working out. So if we take a look, I've redrawn this diagram from above, but what I've done is I've plugged in my horizontal and vertical components. So you can see here that despite the fact that there's a force acting at an angle, there is some kind of horizontal pull and some kind of vertical pull, and only one of those two acts at a perpendicular distance, which would be the Fy force. So the torque is found by multiplying the force and the perpendicular distance. In this case, it's the y component that acts a perpendicular distance, and we found that Fy is just equal to F sine of theta. So the actual torque for this problem would be found by multiplying the force times the sine of this angle multiplied by this perpendicular distance. So all we've done, we just had to take one extra step and resolve this force into its vertical and horizontal components and determine which one acts perpendicular to that axis of rotation. So let's look at a quick example. We'll look at another seesaw type example. We have two forces, a 500 Newton force and an unknown force. The unknown force acts 2 meters from the fulcrum, and the known force of 500 newtons acts 3 meters from the fulcrum. So what we are trying to find here is what force must F2 be in order for equilibrium to exist. So, like we did previously, we will find which horizontal and vertical components act on this system because both of these act at an angle. So this 500 newtons does not act perpendicular to the fulcrum, and this unknown force does not act perpendicular to the fulcrum. We need to find the components that act perpendicular. So I'll start off by finding my horizontal components. I've set up my F1 and my F2 triangle just based on these two diagrams. And I've found my x and my y using trig functions. So 500 sine of 50 degrees, 383.02. The horizontal component is 321.39. Now for F2, I don't actually have F2, so I've had to solve everything in terms of that unknown force. So the vertical component is equal to F2 sine of 63 degrees, which I've just resolved to 0.89 F2. and the horizontal component found using cosine resolves to 0.45 F2. So I've drawn those in to my original diagram. So you can see that my y component pulls up, my x component attempts to pull to the right, and on the left, my x component tries to pull left, and my y component or vertical component tries to pull up. Once I've resolved these and I have my x and y, it's hopefully clear to see that this force acts at 0 degrees to the fulcrum, this acts at 0 degrees to the fulcrum. Those are not perpendicular. The only perpendicular components of force in respect to this fulcrum are the 383 Newton force and the 0.89 F2 force. These are the only two forces that I need to consider. These do not act perpendicular, I can ignore them. So if I want to calculate the torque, I've decided that clockwise will be positive, and it must all equal 0 if equilibrium is to exist. So this force, if I kind of pin this hinge here, and this is the only force, this is attempting to make the whole system rotate clockwise. So that will be a positive torque. 0.89 F2, that's my force. 2 meters is my perpendicular distance. So my force, in terms of F2, times the perpendicular distance will give me the positive torque from this vertical component of F2. I'm going to subtract because I get negative torque, and it's negative because if this hinge was pinned here, this force is attempting to make the whole system rotate counterclockwise. So I'm going to subtract this force times the perpendicular distance. Force times perpendicular distance. That has to all equal 0 for equilibrium, and if I solve that out, I will find that this actual force must be 645.54 newtons in order to produce enough vertical force to balance out this system.